In the present video, we're going to show you how to use the animation abilities of plot2D to simulate the animation of, or to simulate Brownian motion. Brownian motion is the motion of small molecules that are being surrounded and hit by other molecules in the neighborhood, and so the distance that they move in every time step and the direction they move are random. And so we're going to use the plug-in statistical tools to produce random numbers to simulate the motion. Suppose that we have a particle. This is represented by those little circles in there. And that particle at time k is located at this point, whose coordinates are xk and yk. And then in the next time step, the particle has moved by a random distance r in a random direction theta, so that they're going to be now at position xk plus 1 and position yk plus 1 with increment delta xk, delta xy. From the figure, it follows that position xk plus 1 is equal to xk, x of k, no, x of I. But added r times the cosine of theta, that's the delta xk. And in the vertical direction, you have the position adding r sine of theta sub k. We're going to assume that our distance traveled and every time step is normally distributed with a mean mu and a standard deviation sigma, whereas the direction chosen for the motion is uniformly distributed in the circle or in the directions starting at an angle theta sub s, ending at an angle theta sub d. I have a couple of functions here that I'm going to use to simulate that motion. Let me tell you about them. The function will take the mean value and the standard deviation for the radial position, for the radial motion, the starting and ending angle for the angular motion, the number of times that the motion is going to be repeated, and the number of points that are going to be animated. I start by creating a matrix of random numbers between 0 and 1 with n points. So the rows represent each point, and n times the columns represent the number of times that the particle moves. Our theta will be another set of random numbers for n points and n times. And then I'm going to take those values and use the quantiles, which is the inverse cumulative distribution function normal for RR with the parameters mu and sigma for the radial distance. And so this is going to be a matrix of n points, rows, and n times columns, indicating the distances traveled by the particles. And this will be the directions. These are uniformly distributed, so I'm using the quantiles for the uniform distribution with these parameters. And I vectorized it, so I'm getting also a matrix of values. Now I vectorize the product of r cosine theta and r sine theta. That gives me my delta x and delta y. Then I start a vector of n points in one column for x and a vector of n point in one column for y. And then I'm going to be adding to every column the increment in x and every column the increment in y. So by the time I'm done with this for loop, I'm going to have a matrix of positions with n points, rows, and n times columns, and the same for y. And so this function is going to report for me a matrix of matrices. And then I also have a function that is going to produce the graphics for the points. They're going to be points of size 15 and color red, and I'm going to stack them for as many rows as there are n points. Then we're going to join these two together into a matrix that's going to provide for me the position of all those points. So I give these values to the parameters. I'm going to have 50 repetitions of 50 points, angles between 0 and 2 pi, that means in then 360 degrees, with a radial distance that will move with a mean of 10 and a standard deviation of 2. I call my matrix of points, of values, sorry, of position xy, and then I extract the positions x and y, create the points, and then create a function of time where I'm going to take the column of position time t from x and the cardinal position time t for y. Add to that the specification of the points as I did with the function endpoints, and give me a picture of the endpoints at any particular time. I'm going to run this for times 1 to n times. In order to adjust the x and y axis, I determine the minimum and maximum values of y, and that I'm able to change my ranges of x and y in here. And then I produce the animation by writing f of t here. And so what you see there is a picture of the points in every instant, and then as you change instances, the points start moving, and it looks like a cloud of particles that is spreading. So this could be used to simulate, for example, a contaminant spreading out of the point 0, in random directions with random distances, and basically simulating the expansion of a cloud of contaminant. These are basically just the instructions that you need to activate the animation and to change the frame rate if you need to. Those are being presented earlier. And here are a detailed explanation of the animation function. If you want, you can pause at this point and read this, but I already explained to you what every step of this function does, and so you have a better understanding of what's going on. I did an animation here with these parameters, but only 4 times and 6 points. And so this is what you get out of the rwalk function. You get the matrix at the position time, at the first time position, they are all at the origin, and then every column represents different values of time. They have 4 times, as I indicated before, and there are 6 particles. Okay, and so I will extract in the process of producing the animation, as I did here. I will extract this, create the PT, and create the function ft. So that's what I'm going to do here. I extract the x and y positions. I produce the PT matrix, which is just specify the points, and then form the function f of t. To illustrate what this function f of t does for these 6 points, I calculated f of 2 and f of 4. Remember, we only have 4 points. And so what it does is just produces the position of every particle, and then that position changes. And so you can see the animation by seeing different pictures of the particles at that position. I did it for this case. I changed my times to n times, and then I produced the minimum values of x and y, and you can see the 4 positions right there. All the points concentrated at the origin to start with, and then those points moving around. Another thing I did here is change the directions. Instead of going from 0 to 2 pi, that's the entire circle, we're going to go from minus pi over 2 to pi over 2. So basically, we're on the right side of the plane. In that case, you can see that the particles start moving away from the origin, from the y equals 0, but they are moving to the right only because they are limited to that half side of the plane. Another example here from theta from 0 to pi, that would be the upper side of the upper half of the plane. And so the particles spread in the x direction, but they are all moving vertically upwards because they are limited to move from 0 to pi angles. In this case, we make a very limited value of the angle from pi over 6 to pi over 3, which is sort of like direction and 45 degrees right there. And so the particles are spreading because the distances are normally distributed, but they are also all moving in a very limited sector of the plane. And so this is a way to animate a cloud of particles, let's say, and show them moving in the plane, simulating some sort of random Brownian motion, and that's what I wanted to present for this particular video.